You spend the rest of your life living on the ocean. You travel the world's oceans. You'll never see 80% of the water in the ocean because it's down deep, it's dense, and it stays there. So what kind of water is going to be the densest? Cold and salty is going to be dense. Thermocline, decrease in temperature with depth. Halocline, increase in salt content with depth. Pictocline, increase in density with depth. Where would you find the coldest, saltiest, densest water in the world? Starts with capital A.
Alaska.
What?
Antarctica.
Antarctica. Coldest place in the world will have to do with Antarctic water, a later chapter. Raise your hand if you know how to read a triple axis graph. Well, here comes a new skill for you. Let's see if you can handle that. Okay, that's what it's going to look like. Our vertical axis is labeled what? Temperature. Horizontal axis labeled salinity. Blue lines labeled density. The way you work this is you pick one. Let's suppose we pick a temperature 10°C, so that's pretty cool. So we go across to higher and higher salinity. Now the double circle here means they're eliminating the decimal point. Average for the ocean is 3.4. Because they put in thousandths of percents, there's no decimal. Anyways, we go across to higher and higher salinity. We're crossing the blue lines for 1025, 26, 27. Density is going up. So salty is dense. Pick a salinity, let's say 3.4. As we go up the vertical axis toward warmer and warmer temperatures, we're going to cross the blue lines for 1027, 26, 25, 24. Warm water is therefore less dense, cold water will be more dense, and right there in the corner is the densest. You have the highest salinity content, you have the coldest temperature, right there, cold, salty, and dense. Okay? Here's a pictorial review of what we just said. The picnic line effectively cuts out 80% of the ocean from our view because the water down there is cold, salty, and dense. It's a combination. First of all, the thermocline, decrease in temperature with depth, and the halocline, increase in salinity. Any questions? Comments? How big's the wave? A surfer crouched like this is about 5 feet. 5, 10, any figure. The caption here says 13 feet. I think that's a misprint. 43 feet would be more reasonable. You do not learn how to surf here and then go and try to attack back. This is extreme surfing. If the lip of the wave happens to hit the surfer, what happens to him or her? Crush. Where are they going? All the way down to the bottom, which means you have to be able to hold your, and it may take multiple waves to get to come back to the surface. Which one's us, top or bottom? You wish it was the top. The top one up there are called plunging waves. This is due to a short continental shelf where the energy of the waves not eaten up. The bottom one, which we have, is referred to as a spilling wave. That's because we have an average continental shelf and some of the wave energy is eaten by scraping across the bottom. So we're going to start dealing with waves here now. Let's go to Roman numeral 3. And we're going to deal with wind waves. We're over to chapter 10. Not done with chapter 6, we'll be back there a little bit later. And start dealing with waves. You know, you're down at the ocean, having a nice time at the beach, we're kind of being fooled by what we see down there. We think we see a series of waves coming on toward shore. But if you think about it, the water never increases in depth up on the shore. Once the wave breaks, where's the water go? Back out. Suppose you walk out there. You're up to your knees, up to your waist. What do you feel at the bottom besides the sand and the seaweed? No, you get that undertow, you get that current going back out. We're being fooled in that we think we see waves coming on the shore, but there's actually a return action. A tight circular motion sets up. We see the top part, think the waves coming toward us, there's also a return action taking place underneath, which means these are not true waves. We're being fooled. And notice once we get down deep enough, to half wavelength depth, that circular motion completely stops. Submarine. If you're in a submarine which can submerge, why have this bouncy ride on the surface up and down? And all they have to do is submerge down to a certain depth. It's going to be smooth. What's wavelength? How far apart the waves are. So let's suppose that's 100 feet between these two waves. How deep for it to be smooth? 50 feet. That's smooth right now. This tight circular motion, letter A in your notes, is called oscillation. A tight spinning motion, you find out in the ocean, is referred to as oscillation. These are not true waves. You've had some background in sound waves or light waves, whatever. These are going to be a little bit different. We're only seeing the top part. Transfer of energy from blowing air to moving water. Initially, the restoring force is going to be hydrogen bonds. When the wind pushes on the water, hydrogen bonds try to pull it back. You get a rocky motion. Once wind speeds increase more, gravity. As the wind tries to push the water up, water doesn't want to rise, it wants to come back down. Think about a young child on a swing. How do they go higher and higher? Put their legs out going up, pull the legs back coming in, push back out. That rocking action sets up as the wind blows across the water. So let's deal with the parts of a wave. As we do that, we'll also put down the averages or expectations for the motion. Okay. Letter B, let's do wave height. Letter B is wave height. If you've had some background in waves, you probably have the term amplitude instead of height. We cannot use amplitude in this case. Amplitude is that dashed black line you see here. Amplitude says you got no wave at all. When you do get the wave, how far is it from being perfectly flat? For water, we cannot do that. If you're out here surfing, boating, swimming, you've got to deal from the very bottom of the wave to the very top, so we change the term to height. The bottom of the trough, the top of the, what's the upper part called? Crest. Alright, what's normal? Anybody know? Alright, put in your notes, normal wave height for deep ocean wave is less than 10 feet. What? 10 feet? We always hear about 40, 50, 90 foot waves. How are we saying 10 feet? Special circumstances we'll deal with later. Right now, an average, less than 10 feet. How much is 10 feet in this classroom? Ceiling. So, bottom of the wave to the top is the ceiling, which is pretty big for us. We do have special circumstances with you later. All right, letter C, let's do wavelength again. Letter C, wavelength. This is simply how far apart the waves are, or most people use the distance from one crest to the next. You could do trough to trough, doesn't matter. But since the crest is up on top, you usually say how far apart the waves are. So distance between waves is your formal definition. Anybody know what's normal for the open ocean? I put in your notes, 300 feet. What? There's no way surfers coming on the shore 300 feet apart in their waves. Special circumstance. We'll view the beach later. The open ocean, 300 feet apart is average. Again, because of this oscillation, this tight circular motion, we're getting some different definitions and descriptions here in the water waves. Let's go down deep and check out letter D, which is frequency. Letter D is frequency. Now, once you write that down, read what they wrote here and tell me what they did to come up with that definition. What must they do to come up with that definition?